So in this problem, you just asked to write a mechanism for the conversion of 2-propanol or propene to 2-propanol. Okay, so it's simply a mechanism question. That's all. So propene is that, and there is only one possible alkene isomer you can have for this, because there is only one position you can have a double bond. So that is propene, and converting it to propanol means that you're going to have that's 2-propanol, not just propanol, it's 2-propanol. And this can be performed in the presence of acid, catalyst, and water as the nucleophile. So when you have a small amount of acid, the acid is going to attack the alkene bond. That's what we have seen. When you take an alkene, add HCl, the H plus from the acid just goes after the double bond, and the alkene is going to donate electrons to the hydrogen, or actually the proton I should say, and that gives you a new carbon hydrogen bond over there, and that means that your carbon in the middle is going to get a positive charge, because when this pi bond is polarized, this carbon essentially takes both the electrons and gives it to the hydrogen to be able to make a bond. So this electron is still with the carbon, and this carbon's pi electron is now going to be with the hydrogen, so that you can make a new carbon hydrogen bond, and that leaves this carbon in the middle with a positive charge. And once the carbon gets a positive charge, which is what we call the carbocation, it is going to need to take care of the positive charge. That means it's going to polarize the electrons on the nucleophile, and it's going to make a bond with the oxygen, where oxygen gives both these electrons towards making the bond, and that is what we end up getting, where this new bond here comes at the expense of oxygen donating both electrons. So that electron is close to oxygen, and this electron is now with the carbon, which means the oxygen is going to get a positive charge. And again, if oxygen needs to take care of its positive charge, it is going to steal electrons from this hydrogen here, and that ends up breaking the oxygen hydrogen bond, where the hydrogen is going to be kicked out as H plus, and you have your alcohol here, and this proton is essentially going to make sure you have a balance in your concentration of H plus, because before the mechanism started you had one H plus, and the H plus was consumed in the reaction mechanism, and at the end of the mechanism one H plus is being kicked out. That means it's going to go back and perpetuate the cycle to continue the catalytic process of converting your alkene to the alcohol here. So that is pretty much what you need to know for the mechanism for conversion of an alkene to an alcohol. And in this problem, we again have a reaction of alcohol with a bunch of reagents. So we'll look at the various products we will get, and in some cases we will see what kind of selectivity you will get. So you have 2-methyl-2-butanol. So this is 2-butanol, and it also has a methyl on the second position, so that is a tertiary alcohol, and that reacting with HCl means that the HCl is going to release H plus and Cl minus. H plus is going to protonate the alcohol, make it a good leaving group. Alcohol leaves, you get a carbocation, and then the Cl minus makes a bond with that. So the product is going to be 2-chloro-2-methyl-butane, right? That's a product. And 3-pentanol is that, and when you react that with sodium, we are going to get sodium pentoxide, and you're going to get half hydrogen released as the byproduct. Alright, and if you have cyclohexanol reacting with PBr3, we have seen that thionyl chloride and phosphorus tribromide, they are going to both give you the corresponding halogen as the product. So if you have PBr3, you're going to get bromocyclohexane as the product, and essentially you have 3 alcohols reacting with PBr3 to give you the trihydroxy derivative as the byproduct. Alright, so you get 3 of the alkyl halide and POH thrice. Okay, and here we have phenyl ethanol, so that's ethanol, and we have 2 phenyl ethanol, which means the second carbon is going to have the phenyl ring, and when that reacts with thionyl chloride, SOCl2, you are going to convert that to the corresponding alkyl chloride, so it's going to become that. So wherever you have your OH, you're going to get the chlorine on that position. That is that. And here we have 1-methyl cyclopentanol. So we have a cyclopentanol, and on the first carbon we also have a CH3. That, and if this was just HCl, like we saw in the previous problem, or if it was just HBr, then your answer is going to be that. Whereas when the same question says that you're using sulfuric acid with heat, especially if it's concentrated sulfuric acid, that's the right way to do it. You cannot use diluted sulfuric acid for this reaction. Concentrated sulfuric acid and heat means that you're going to have a dehydration reaction. You have a dehydration reaction. That's because your concentrated sulfuric acid is going to protonate your OH, and it's going to become OH2 plus. I can just discuss this really briefly. So when your alcohol is protonated, it's going to get the oxonium ion. This is a really good leaving group, especially that you have a tertiary carbon, and that's going to produce a corresponding carbocation like that. And you don't have any nucleophile in the medium, because concentrated sulfuric acid is a medium where there is absolutely no water, and any water that is there is completely sequestered by sulfur trioxide to make sulfuric acid. Therefore, the only fate of this carbocation is the loss of a proton to make a double bond there. So you're going to get an alkene, which is what we call the dehydration reaction. So you take concentrated sulfuric acid with an alcohol, especially with a secondary or a tertiary alcohol, you're just going to form an alkene, and you'll be getting the Zaitsev alkene in this case, and heat is going to just make this reaction go more efficiently. Right, so if you have a halo acid, you're going to have the corresponding alkyl halide, but if you use sulfuric acid or sulfuric acid phosphoric acid mixture with heat, it's going to give you dehydration reaction, which is going to be a loss of an OH from here and H plus from there to get an alkene. So that's something that you definitely need to make sure you distinguish between these two acids, right? Okay, and ethylene glycol, I didn't really discuss this reaction, but to kind of quickly mention, when you have a diol or a triol, especially react that with nitric acid, you're going to get the corresponding nitrate. So you're going to get that. So you're going to get a dinitrate as the product of this reaction. But I didn't talk about this, so I'm not going to ask you any questions about this in quizzes or exam. So just ignore this. But since it's here, I just discussed it really quickly. Okay, and if you have an alcohol with HBr and zinc bromide, which is what we call the Lucas test. So 1, 2, 3, 4, 5, 6, 7, 8. And you have an alcohol with zinc bromide and HBr, you're going to get the corresponding halide. So if you use zinc bromide, you're going to get the bromide as the product. That's pretty much all you need to know. The role of zinc is to make this OH a good leaving group so that you form the halide efficiently, because zinc is zinc 2 plus. Sorry. Zinc is going to be zinc 2 plus, and that coordinates with the oxygen, makes a bond with the oxygen, and makes this a good leaving group. So Br minus can take its spot to give you the alkyl halide. Alright, and if you use 1-pentanol with aqueous sodium hydroxide, we know that it's simply going to give you the alkoxide, O minus. Alright, again, that's something that I discussed in one of the earlier questions. So that's all you need to know. And if you have 1-pentanol with chromic acid, so that with chromic acid, it's same as what we call the Jones reagent. So chromium trioxide is not chromic acid, chromium trioxide I should say rather. In the presence of a strong acid like sulfuric acid becomes a very strong oxidizing agent, and that is what we call the Jones reagent, and that is going to give you first an aldehyde, and that aldehyde will be further oxidized by the chromic acid, because as I told in the classroom, you're not going to use a limited amount, you're going to use an excess of the chromium trioxide acid mixture. That means the aldehyde will be further oxidized to give you a carboxylic acid. So that's the product of this reaction. And a 2-cyclohexane thiol, 2-cyclohexyl ethanol is this. So this is ethanol, 2-carbon alcohol, second carbon you have cyclohexane, so 2-cyclohexyl ethanol reacts with PCC, so pyridinium chlorochromate, and that means it's a controlled oxidizing agent, and it's only going to give you the corresponding aldehyde, and the aldehyde will not be further oxidized by PCC to give you a carboxylic acid. So you will just stop at the aldehyde stage. So that's all you need to know for this.